Forward to the cloud. Awesome. Thanks, John.
Sorry about that.
All right. So I'll do a quick intro for you, John, and we'll pass things over. So John is a senior geophysicist with DS Geophysical, the research team and development team, and he is also going to be joining us here at UBC. Really, really excited about that. And he's also a very active and core contributor to the SimPeg community. And so his talk today will be on leveraging convolutional neural networks for time series quality control. So I'll pass things over to John, and maybe he can also introduce his co-presenter, Charlotte.
Hi, everyone. Thanks for attending. Charlotte and I put together a little tool to help us with our day-to-day jobs. And yeah, Charlotte Thibault is a project manager of the processing department, geophysicist by trade. Want to say a couple words there, Charlotte?
Oh, hi, hello. Yes, so yeah, John and I have been working together for the past 7 years. I had to calculate that. 7 years. We pretty much built the processing department at here at DS, for all this time. And yeah, just sitting next to each other, we've been bouncing ideas of each other for the past 7 years, and that came to a conclusion with this new tool, so that we're excited to present to you today.
Nice. Just a little bit of a disclaimer. I'm just an amateur machine learning enthusiast. This will be like more of a high level talk, more of like the applied side of it, because this has been a project in the making for quite a few years now. We've been tinkering and toying with it. We just have so much data to work with, and I know this will be my second talk where it sounds like I'm complaining about too much data, but this is the way that we figured out how to tackle it. It's been a tough time going through it, but we finally got something going here, which is quite nice. So we're going to start right from the beginning of our motivation. So typically, this is kind of what you'd be looking at for nice 2D section, DCIP. Nothing too much other than your QC. I guess QCing DCIP data has long been used to calculate apparent resistivities, chargeabilities, and because these were traditionally they were the only recorded information you just output from a text file from the instrumentation. But this kind of made the more of an art way of tackling the task. Like, oh, okay, well, we got to smooth these out. There's some outlier points. So it was the geophysicist trained eye that would identify the outliers based on how much it looked, how much it standed out from the other points next to it. But that was like little to no other information to support this choice, nor an easy way to identify or neutralize the problem. Sure, you might have a quality factor attached to it, or just like an error number, but where does that all come from? How do you determine those? So now with the new instrumentation, we have time series readily available. So now we can click on those points, those outliers, and we can see what makes up that value. So we're still basing our QC calculated apparent resistivities and chargeability data, but now we can dig a little deeper and make a better educated decision on these points. So by analyzing these raw time series, identifying false positive information is possible, like correlated noise or intermittent noise during the recording or during the acquisition. But then we move into the 3D atmosphere and things get quite messy. You have a lot of 3D azimuth data. The task gets a little bit difficult because you're starting to look at so much more data, and you can't just look at it in a nice little 2D plan map fashion. It all depends on where your injection is, it just depends on your geometry, really. So maybe you could go through and select all the 40-degree angles or the 60 degrees or the inlines. But again, that's going to be time consuming because you're going to be you got to pull these all out and look at them all individually. So right now, the current quality control workflow here is, up to not too long ago anyways, the DS's general QC flow involved processing the entire data set, followed by noise correlation analysis and null coupled and outlier data removal. Just kind of expanding on the existing 2D stuff, keeping everybody kind of familiar with things. So we've generally been kind of moving into different ways of QCing. And then after that, we would go using the residuals from our inversions. So we kind of leverage the inversion to give us a little bit of a feedback loop so that we can fine tune the QC by highlighting additional outliers that weren't fitting the data or anything like that. And but this workflow presents a lot of shortcomings because now you're in a feedback loop with big data. Inversions don't happen that fast. Well, they do now with a little bit of work that we did previously, but they're still quite rigorous and takes a little bit. So the first entire, the QC as it is, the first entire raw data set is processed without distinction. It just grabs all the data from all the receivers and just computes, makes up your nice sections and your resistivities and your chargeabilities. And that's going to eat up computing time because you're going to be computing like bad dipoles. You don't know if they're great or not. You're just throwing everything in the sink with it and see what happens. Noise correlation is not also a silver bullet. Two disconnected receivers can have a high correlation score. Reversely, two receivers forming a dipole could have low correlation score because their individual waveforms exhibit uncorrelated noise. Yet, specific to DS here, when we do the subtraction to make the dipole, that stack signal could look okay afterwards. We just wouldn't know because it would get stacked out or filtered out. But underlying, there is this uncorrelated noise. So relying on manual outlier removal and inversion residuals, identifying bad data points is very time consuming. I just kind of touched on that in the last slide, and can come across as a little too late in the process. After you've gone through inversion, that could be days when maybe we needed to know that it was a bad receiver and that receiver is still out there collecting data. So hopefully we can speed things up and we can spot these things. And then, if there was only a way to handle this all in the upstream. So bringing it back to basics, this is what our data that we look at and traditionally use, apparent resistivities and apparent chargeabilities. So it really all comes down to, bringing it back to this. And we QC these values because it's the way it's always been. And yet 3 out of the 4 variables here include a calculation from the values that are they included are the calculation of the values from the time series. They're all derived from the acquisition. So let's start there. And just in a little example of digging a little bit deeper behind data, like this one here, this is not the greatest. It's got a blowout at the end, but the stack data, you likely we're going to pull out a good DC value out of there, or a decent DC value that might not be an outlier. But if you actually look at the raw time series, you see that you're going to have, you got some bad data in there that's going into the full resistivity calculation. So we kind of want to avoid that, but at least with the full time series readings, we can take a look at that and we can find it. So our thesis here is that earlier we can identify and quarantine bad time, or the earlier that we can identify these bad data points and quarantine them, the faster and more reliable the data processing and quality control can be. In addition, a new wide range of information and stats can be extracted from the systematic waveforms. We can get a better sense of the on-time noise or just look at the off time. We can do some fun statistics and pull out some data or some information for the geophysicist to help make a more informed, educated decision. But the new problem arises. Scanning through thousands, if not tens of thousands of time series every day is certainly not something we could subject a human to. We try, but it's quite tiresome. So in order to get the quicker turnaround in the data, what if we trained a computer to do it? So Friday to the rescue. We coined it as first rigorous initial data analysis yet. So it's the first go. Actually, originally we got the name from, we were thinking of Iron Man in the first episode, or the first series there. That was the AI there that he had originally, but we adapted it to our own. So by automating this time-consuming task, the raw time series analysis, we can pull out extra information, and now the data processors can start with a much less daunting task. Like for example, this is from some of the test runs that we did, or when I was just kind of getting it up, so not quite in production. So Friday does add like another step into the workflow, but it rather blends into the workflow. So it reduces the time instead of increasing it. For example, here, our standard workflow, I created 8,437 dipoles. It ran in about 4,200 seconds. And this is what you get. So the geophysicist would sit down and have to go through all those data points. But now we include Friday and we get less dipoles and the time is reduced as well to 32 or about 3,300 seconds. And then now the geophysicist data processor starts with this, which is a much cleaner data set. Still has, you know, some noise in there and whatnot, but that's a lot less daunting of a task than the first one. And yeah, so you're doing less dipoles, so of course you're going to have less time to do it. But we've actually added in another step. So that's what's kind of the key thing here is we've added in what would seem is a much larger step, but we're actually reducing everything. But that's partly in order because we don't have to process so much negligible data. I lost my mouse, sorry. And then, so here's an example of actually in production. So our standard workflow again, 43,000 dipoles. That's quite a lot to start going through. We got quite a bit of poorly correlated receiver data versus adding Friday into our production workflow. And now we have, significant, noticeably enough, or reduced dipoles and reduced correlated receiver dipoles, or poorly correlated receivers. And
hey, John,
yeah.
Can I assume that what you meant dipole is the number of DC data, or like is that?
Yeah, that'd be DC and IP data. Yeah,
I see. Okay.
Yeah. Right. I'm just kind of plotting the DC right now, but yeah, those are both brought out, of course, at the same time. So yeah, so having this nice cleaner data sets and having an automated kind of script that kind of does this, Friday can continuously look at data as it's uploaded from the field. So we don't have to actually even start it. We can have it as a trigger. So as soon as that data comes in, it's looked over by morning, the data processor sits down and he's got a nice cleaner data set and ready to go. Hopefully doesn't have to spend all day doing it. So let's take a look at how is Friday doing this? What's under the hood here? But I'm going to start with the story from the beginning, how we started to do this. And yeah, so Charlotte and I, like she said, we've in the beginning days, we had a small office, so we were sitting beside each other, and yeah, we had a lot of work to do and a lot of long days. So we started throwing around what's the solution? What can we do? And machine learning was just coming up, and people were ranting and raving about that. So I started to look into it. And I started with kind of the scikit-learn, just a simple keras sequential building a neural net. I've always tried to keep everything simple. I didn't want to go into like many layers, how much just try to keep it simple at first, just to see if I can get anywhere in the ballpark. So yeah, kept things simple. Created just like a simple 2 dense layers and a single feature layer model. And yeah, a couple of different kind of activations or optimizations. Yeah, just kind of played around, see what we could get. Oh yeah, okay. So yeah, that gave us a nice little model to work with. And as you can see on the side here, our training data. I used the full time series data, so the entire thing. And at DS, we have endless amount of data. There's more than enough there. So why not train on it? Well, we can avoid going to synthetic data. We can just go right to the source and hopefully add in we don't have to actually add in any noise. The noise is real here. Hopefully Friday can learn and characterize noise in that sense. So yeah, first of all, I went just looking labeled data as in stuff that we always kind of encounter, EM coupling, timing issues, the receiver not grounded, it's just like an animal hit it and it's just laying on the ground, variable or transient noise spikes, just bad contacts, tellurics, or just plain bad, like this one here. Like, yeah, who knows what's happening there? Some bad stuff. So let's see if we can get it to spot those things. So Friday and its first guess ever here. And it got it right. So that's pretty exciting. But you can see here in the bottom, it maybe isn't overly stable because we can see that between contact and bad, it's kind of having a hard time distinguishing it. The scores are quite high on both of them. That's going to be a little bit important later on here in in the talk. But yeah, you can see, you know, there's a lot of scores. It's really zoning in on any of them. And that came to conclusion, after testing accuracy, it was only about 74% accurate. So yeah, it was doing it, it guessed right, and it does an okay job, but it's, yeah, and unfortunately in the end, the model was just not stable enough. So the project was shelved for a bit and back to the drawing board for me. So next came up was, hey, let's look at convolution neural networks. And this was, I got onto this from the esteemed Dr. Lindsay Hagee. She recommended CNNs and PyTorch. It was very useful to a problem that she was using, or that she was applying it to. And yeah, so I was like, oh, well, let's take a look. And by chance, I was out of the country on a job right when COVID hit. So upon arrival back to Canada, I had 2 weeks of sitting around. So I grabbed a book, or a PyTorch book, and deep learning, and spent the time going through some math, trying some problems, and started to work on it. So I ended up with a simple convolution neural net. That's just for now. This is work in progress as well. So just something simple, one convolution layer, 2 fully connected layers. This example here is a brief example. I haven't found where you can draw all these cool things, so I couldn't make one specific, but this is closest to the representation of what we have right now. But yeah, so this alone started to find sufficient classification and accomplished, we accomplished this with just a single layer and 2 fully connected layers. Optimizing things a little bit, playing with the optimizers or the activations, we were getting around 94% accurate already. It jumped up right from that 74% pretty quick. But yeah, this is also like a focused. We didn't use all 8 classifications. I just started with a specific kind, or sorry, a specific set, and most of those are getting 99% trained, or on training data, it gets 90% accurate. The only ones that suffer are like the EM coupling. That's a little bit of a tough one because some generators, or not generators, transmitters can have some odd spikes at the beginning and do some stuff that kind of confuses the neural net. So there's some work to be done there. But overall, 99% was pretty good for most of the labels. But yeah, so maybe, playing around further will prove more fruitful for some of the other labels, discriminating the other labels. Yeah, so after building the model, I just went with a simple the rectified linear unit activation function. This one was said that it helps models account for interaction effects, nonlinear effects. And yeah, I found from when I was playing with the neural nets alone that this one was kind of most fruitful for the application here with these time series. Softmax, it was okay, things like that, played around, but this is the one I ended up choosing anyways. Yeah, it was found very effective in my first attempts, so I just haven't just moved on from there. Not yet anyways. Yeah, so now let's look at what we did for the training of the neural net. We kind of stepped back and we took a different approach. And Charlotte was the one who suggested, she's like, well, why don't we use shorter segments? Stacking is only on the half periods. So let's just concentrate on that. So we broke it down, and now we're just looking at full period. We went with the full period so that we didn't have to go through, cut up even more, and then reverse the negative on time polarities. So yeah, we just went with the full period, and that's ideally what we're concerned about, because that's what's going into the stacks as it's processed. So though it's using half periods, the full period at least gives us a little bit of an advantage on hopefully having Friday look at longer, lower frequency noise. Not quite really low tellurics, but yeah, it's something that'll kind of go through a whole period, kind of a wave. Hopefully we can get it to identify. So I think that gives us a little bit of advantage, not cutting it too short. And yeah, so the learning and training data sets, I focused on 6 primary classifications. So good. This is a good waveform. You're going to pull out a good VP, good secondary voltages right there. Second is just bad. You mostly just trying to do good, bad, good, bad, good, bad. But there, of course, is other refinements, as in EM coupling is also a one that we see quite a lot, especially in the lower states. Yeah, actually, a lot of conductive environments, you're going to see this stuff. And although we won't throw these out, it's nice to have Friday identify them and then let us know, like, how much EM coupling are we observing on the property or on the acquisition. Yeah, it's just very useful to have. And then we can kind of maybe make a quicker informed decision on what IP gates to use, so that we know that we're well past the EM. The fourth one is a common one for us with when you have data loggers, a sample or time shift. Sometimes it'll lose sync. There'll be a hole in the satellites and the timing just goes out a little bit. When you're looking at full time series, that's kind of hard to identify unless you zoom in and you actually look at the times and then line everything up. Whereas Friday, we're teaching it, hey, find that out and let us know. And then the next important one would be contact. That could be caused by a variety of things: animals walking over the wires, knocking the receivers, just knocking the electrodes loose, or the wires that are from the electrode to the receiver. And then you end up with, at the bottom here, nice squiggly, noisy data. So we should be able to train it on that. Train it to identify that. And then variable, just kind of like an outlier, not sure what, this is also a sample issue, but this is also, just something weird that's happening. Variable effect. Hopefully we can try and train it on something like that. So in all, each full period sample is determined by 8 possible labels. So I'd still use 8 possible labels, but we focused on the 6 so far. And these are going to be good, sample, variable, EM, contact. We're going to add in transients, disconnected, and bad. Right now, the disconnected isn't as important since we're looking at all full periods in the time series itself. We have a classification for the whole time series, and we can see it's like good, 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 and then all of a sudden there's bad. You can see that, oh, this node is disconnected. So it's kind of like in the back end, it can take care of it first before we even have Friday identify it. Though when it happens in the middle of a half or a full period, we're going to need it to teach it that. Hopefully it'll help out a little bit for that. So the training data for what I've done here so far is just 10% of the learning set. That consists of about 11,000 labeled segmented data. Some classifications, as I was saying, still need more training, like that contact and the other like disconnected transients and whatnot. So since this is not synthetic, the hardest step actually towards all of this is automating the learning data set creation. So I manually built this with a little bit of computer assistance, but I used to have to take the SkyTrain every day. So as I'm on my way to and from work, just sit there and good, bad, blah, 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 and built the data set. So really that was the most time consuming part and still growing. The more data, hopefully we can help discriminate some of those other ones. Maybe 11,000 just isn't enough for some of those other classifications. The training involved 2 loops, just 2 epochs. The loss decreased already to an acceptable level. Model looked stable. Guesses were acceptable, and it did the job rather quick. I was using the cross entropy loss function, the stochastic gradient descent, and some atom optimizers. Still playing around with a bunch of that stuff because, finding some interesting results, as you'll see here. So the one that I have in motion right now, kind of what most concerns us is, of course, the good, the samples, EM, and bad. But you can see the EM it's having a little bit of trouble, like it's only 79%. But as I was saying, it's a little bit hard because if you got like transients, they're kind of going to look like a spike too. But maybe with more data and more discrimination, Friday will learn where those points for the EM coupling happen, and we'll discriminate a little bit better. Because some of the pieces that I've seen is, again, like the transmitter, it has that spike at the beginning, but then nothing on the off time and whatnot. And it's almost random. It'll be like, oh no, that's EM coupling. Oh no, that isn't. So it needs to be further just discriminated a bit there. But yeah, it lowered a little bit of a lower learning rate, but it was still quite stable. And yeah, worked. It's doing the job pretty well right now for what we're concerned. Just like a first pass go, just looking at purely bad or purely good kind of thing. I did go into the atom one, which was kind of interesting that now we've got the contact coming up. So if you remember back a few slides, the bad and contact were almost scored the same. So the atom optimizer kind of highlights that this is where I need to concentrate on some of the discrimination. And it's funny because it took some of the bad accuracy and brought up the contact. So yeah, the optimizers are probably another place to look at as well to help out with this. But this is just recent. I haven't quite put this all into full production. Just when we need to define things a little bit more, I'll take a little bit further of a look. But that's quite interesting to see the correlations between some of the classifications. I guess even by just changing the optimizer, just seeing how that happens. It's quite interesting.
John, can you elaborate a little bit more about like a 0%?
Okay. Oh, sorry. Yeah, the 0% ones are the ones that I'm not really training on right now. They're in there from the beginning. But yeah, in the learning, or sorry, in the training data set, I just don't have any variable or transient or disconnected nodes right now.
Oh, I see.
Yeah, so it hasn't learned them yet is what happened there. Yeah, sorry, I should have clarified that. Yeah, so these are just the focused ones that I'm using right now. Yeah, I did have to use a little bit of or I had to go up an order of magnitude in the learning to get it a bit stable, but that should still be acceptable enough. Yeah, and I had some examples here, but my computer with the work on it decided to die. So unfortunately, I only have this quick example here of that blowout that I showed you before. This is kind of like overall what Friday does. You give it into a time series, and then it just spits out. Sorry, those are just the first 4, but down here, so 3 is EM and 7 is bad. So you can see that, you know, Friday does identify, and it does do quite a good job. And hopefully in the future, we can actually still relay, like I'm storing this data, but maybe we can incorporate it into the processing flow so that when you go to stack the data, it'll read what the predictions were, and it'll just leave those 2 out at the end. Sure, there's other techniques like statistical rejection processing that can do that, but then again, it depends on how high or how long your time series is. If you got 10 minutes time series and you're fitting curves to the off time and then looking at the on time, doing statistics there, it takes a long time. It actually adds up quite time consuming. But yeah, sorry, I couldn't cut to some examples. Technical difficulties. And yeah, so next, the conclusions. Yeah, we can successfully classify DCIP time series. Yeah, it's doing quite good work for us, saving our data processors time and getting some sleep at least, which is nice. So yeah, Friday works. Yeah, so hopefully by adding more layers, various optimizers, modifying feature layers, more learning data, we can refine some of those classifications, like some of those ones that were 0%. I can start adding those in and we can discriminate along them. Yeah, spend more time on the learning data set. In theory, if we have more and we can help, that should help stabilize the additional classifications. Yeah, and then rigorous time series analysis just helps improve the picture, or really. I don't know if is it improving the art or is it just removing the art? But if I'll quote Rick and Morty, Morty said, or Rick says that science is a lot more art sometimes than science. So we'll leave that up to you guys to decide. So we're not able to quite remove the job of the geophysicist yet. So don't be scared, but yeah, the data processing and the data QC now have at least an assistant or something to help them get through the data. So geophysicists and data processors can now sleep and rest. So yeah, and I guess going forward, yeah, hopefully we can, yeah, it just kind of unload all of that load off of the data processors and the geophysicists so that they're more like looking at stats, looking at the whole picture, looking at the data, you know, which days the kind of noisier than the others. We can pull out so much more information this way and so much more analysis. And possibly and mostly in a quicker fashion, which is Yeah, it was good. So yeah, I'd like to say thanks to Dias for, they got all this data and I get to play with it, and they allow me to look at some of these cool problems and solve them.
Thanks, John. Great to know some geophysicists and data processors can now get some rest. Yeah, so we'll open it up for questions, discussion points. Please feel free to turn on your camera. Feel free to just jump right in. We're a small group. If you are having any issues connecting, feel free to put things in the chat and we can relay that. But yeah, we'll just invite people to unmute and jump on in.
Are we live here, Joe? Hey, John, that was a great talk.
Oh, thanks, Doug.
That was really good. Yeah, I'm kind of excited about that with respect to some of the work that Mike Mitchell was doing years ago. I've got a couple of things.
Yeah.
So if you train your algorithm, so then how versatile is it? If you have a different survey, if you use a different pulse rate, for different frequency for your data collection, how many things are sort of transferable, or at what point do you need to retrain?
Well, so far I think the benefit that we're having is we're training on real data. So as we've been going from project to project, we don't notice, or we see a lot of transferability, quite consistent in the guessing. Well, on the focused ones that we did, of course. EM coupling, that one's going to be a bit tricky. Yeah, we're going to have to do a little bit more training and discrimination on that one. But as in regards to frequency, yeah, that's kind of a weak point right now. I need to find, like right now, I'm training it on the frequency that it needs. So hopefully there is a way that we can kind of generalize that, or maybe interpolate the training data set as it is and, expand it, add data points to make it act like a 3-second or a 2-second time base. But yeah, primarily we just do 2 seconds, and that's what the training data set is right now. I'm building up the 3-second, but then again, when you look at it that way, yeah, it's not very transferable between frequencies right now. You actually have to build a training data set for that frequency, unfortunately. But maybe there's a way. Some stuff that I'll be experimenting with for sure. Okay.
Then the other thing has to do with your training. You're working with field data, which is great.
Yeah.
But could you augment those with some synthetic data?
That's definitely something Charlotte and I were talking about. Yeah, completely. I'd like to try it. I was a big believer in just using like the raw or the real data, because yeah, that it'll just like help train with the noise. But yeah, it's really hard to make these training data sets. So synthetic is definitely going to have to play a part in it, I would say. Yeah.
Well, it gives you some extra control on what you're actually, mucking up as far as the signal goes.
That's a good point too. Now we can with the real data, we can maybe apply that into the synthetic data, like you said, to we can muck up things on purpose to have it simulate that.
Anyway, that was great. Love it.
Oh, Shandor? Oh, there's somebody. Oh, Shandor, you're muted there. Still muted. There you go.
Oh, thank you.
Yeah.
It was a great presentation. And I don't know the software that you use, but normally for convolution neural network, in 95% of the cases, they use the LNet or the UNet.
Sorry?
For convolutional neural network,
yeah,
in 95% of the cases, they use the LNet neural network algorithm or the UNet.
Oh, the UNet.
Is it UNet or the LNet?
It would be, I believe it's the UNet that in PyTorch. Yeah. Yeah.
And my question is that when you have the convolutional model and the layers, and then you use the activation function, you have to add some bias.
Yeah.
And how do you decide that how much bias you want to give to the model?
That seems to be taken care of kind of in the background, depending on your learning rates and yeah, just how you, I guess, yeah, I don't got an exact science to how I've set that, just kind of played with some numbers and just found what worked kind of thing.
See.
Yeah.
Yeah, and my last question is that do you think if you used more layers later on, will it improve your results?
Yeah, I believe so. I haven't got to play with that too much yet, but that's what I was going to do with the EM coupling side. I was going to maybe add some more layers, see if that kind of gets, maybe jumps it up a little bit, or maybe it reduces it, at least get something, poke at it and see what happens. And then we kind of judge from there. But I seriously think once we start adding in a little bit the more refined stuff like transients, yeah, trying to tell the difference between a transient and EM, we're probably going to need a little bit of help, and hopefully more layers will help with that as well. Or maybe even adjusting the feature layers. Yeah, increasing some of those features or decreasing, see what happens, kind of thing.
Thank you, John.
Yeah, thank you for the question.
John, that's great talk. I really enjoyed. And I was actually curious why you kind of made the multiple classes. Say, in practice, I guess, on your end, you don't really care whether there's even EM coupling or like bad contact noise. Like at the end, what you care is bad or good. Again, so is this a signal or noise, right?
Yeah.
So I was curious, like actually putting multiple classes was actually useful in the kind of getting a better accuracy, because you ended up getting pretty good accuracy.
Yeah.
For 95%. So was it like if you actually have just broken apart as a 2 and then did the same training algorithm, do you think you would get less accuracy? Or just curious, like why you did it, and then is there make any improvement or
yeah. I totally understand. Like, yeah, for the purposes of going into like, analysis, inversion, good and bad. That's kind of just what you need. And that's kind of what I started with. And it was okay because it identified that I'm looking for a square wave, and that was simple. Everything else bad. But, some of those EM coupling or really low signals, they would sneak through. So yeah, it wasn't perfect. The accuracy kind of went down, and that might have been what was happening with the neural nets as they were, just because it was looking at too much, and it just couldn't represent or couldn't discriminate between the two. But to answer your question about why, is so not only are we looking for it on the inversion side or like the back end downstream stuff, but also at the acquisition level. As the data comes in, we collect this information, and it is actually good for the geophysicist or the data processor to identify, oh, wow, I've got a whole bunch of EM coupling here. What am I going to do with it? And then as the days go on, you can see if the EM coupling changes. You can change, maybe you're doing a pole-dipole and the EM is not going away, and your Friday is just spitting out, oh, hey, we got lots of EM. You might switch to a dipole-dipole. So it helps also to inform at the acquisition level on what you should do. It'll tell you maybe there's a receiver out there that's actually got bad firmware or something's wrong with it. Instead of having that going through and just being kicked out, you want to recover that data. The data processor will be like, oh, wait, this node is very consistently bad. It has a problem. Maybe it's just not connected properly, or just plain bad. It's information that they can relay back to the acquisition in the field, so that we can collect better data and more of it, kind of thing, instead of just collecting it all and throwing out whatever is bad.
And other thing, so you're actually at this point, you're working at the dipole level, right? Yeah. Like, so at a location, there are many time channels, but you're either, okay, this is bad or not, or like there are many sort of classifications. But have you thought about like working at the like a more fine-grained level, like a time channel level? For instance, each time channel data. But then at the end in the inversion, like maybe you have a dipole, but some channels are contaminated and some channels maybe not.
Maybe not.
So like, have you thought about like at doing it in a time channel level? And then
No, well, we were looking at maybe applying this to like helping discriminate decays. Because yeah, looking through tens of thousands of decays isn't fun either. But yeah, no, I didn't actually think about breaking that down even further into the time channels themselves. That's actually could be pretty beneficial. Like you said, depending on, or I guess in like say the time domain or airborne stuff, if you want to just focus on certain channels, that very well help. Yeah, could be a very well applied there.
thanks, John.
Yeah, no, thank you.
Hey, John, have you thought about using any unsupervised learning or just sticking with the supervised?
I've just been sticking with the supervised right now. Yeah.
I was just going to say there's a recent article in Geophysics that's pretty interesting.
Yeah.
With an unsupervised approach to decay curves. So it could be something worth looking at.
Oh, interesting. Yeah, I'll have to get that from you. That link or yeah, what that title was. Because yeah, like I said, I'm an enthusiast. So if there's something else, yeah, I'd definitely get my hands on it and play with it.
Sounds good.
Or maybe there's something we could look at in the summers here.
John, I was wondering, when you started off your talk, you showed a traditional kind of workflow procedure for how you try to contend with all of the noise in the data, and one of those end procedures was get rid of his data that are obviously bad, but then go ahead, invert it, and then look at the residual, and then make some judgment about the validity of that data, depending on what the size of the residual is.
Mm-hmm.
But I'm wondering so now you go through and you have a different way of kind of extracting a high quality signal, and you go ahead and you invert that. Is there anything, information from the misfit of the inversion of the clean data that you could make use of the techniques you previously had to try to help find something? Or I guess I'm wondering is there any sort of feedback to using the results after machine learning, within the process that you had before you even used that?
Yeah, not right now, there isn't, but that's what kind of going into the future. I'm trying to build in so that we can take that information upstream when we actually do the stacking, and then we only stack the actual good stacks out of those signals. We don't actually have to throw out the data that has some bad data in it. We can kind of, I guess, salvage what we can of the time series that were, put through Friday in a sense. I think analyzing the residuals will always come through. It's just a nice check because there's multiple cases where things can look great and then you come in the inversion and it's like, whoa, wait. Most of those are usually geometry, but I think there would definitely be room to feed that back and then correlate it with some of the Friday information.
Thanks.
Hey, John. I really enjoyed your talk. It's definitely nice to see, somebody doing some more of this work. And it seems really promising what you can do with these time series. I was just curious, like the time series you guys are using, is that mostly a time series of the voltage?
Yeah.
Do you have also like time series of like the injected current or like transmitter power or some things like that? And have you looked at any of those? Because I remember when I was playing around with some of this, I just had kind of my single DC measurements. I didn't have any time series to work with, but I did have a few of these other like transmitter powers and things like that. And with some of my work, it did help to kind of look at some of those other parameters to be able to say, okay, when I have like high measured potential differences, but like low transmitter powers or low injected currents, that's a good sign that I have this problem going on. So I was just wondering if you've looked at any of that and if that might be able to help you kind of discriminate.
I've definitely thought into that. However, so we do also have the current as well. But I kind of treat everything the same. As in, like it's all just a voltage time series, and it just looks through the transmitter itself and does the signal, or it tries to label it as good or bad, because usually that's the only thing that you'll see in the transmit. But I haven't got to the point of actually integrating all that information, like pulling out the amplitudes. I do have like a statistical setup that'll kind of compare all that, like voltages around like where the current is, what the voltages look like, and kind of plan maps. But yeah, nothing actually that far along yet there, Mike. But that's definitely definitely something that needs to get in there.
Cool. Cool. Exciting stuff.
Yeah, thank you.
Do other folks have questions? I had one, John, with respect to sort of your bad class.
Yeah.
How variable is it? Because I understand it is kind of a bit of a garbage dump in a sense.
Yeah.
Is it extremely variable, or
Yeah, it's extremely variable for sure. And I think that the plot we're showing, like the scores going to contact and bad, that kind of shows how variable it is, because as soon as you change things a bit, all of a sudden it's thinking that it's something else. It goes from bad to contact, or contact to bad. Definitely it's a little, like, best word you said, yeah, it's kind of a garbage dump. It's just like, that's where everything goes, where it doesn't have quite a feature to it, like a spike or in like transient spots, or a square wave. It's like anything that doesn't have any of those other things, throw it in there. So far that's what that is. But again, yeah, maybe like hopefully with the more layers, playing around, fine tuning the model, more learning or more training and learning data. Yeah, hopefully we can transform it from a garbage dump into something a little bit more refined.
Well, I think it's really interesting to see, because I think, as we think about trying to use synthetically generated data and things like that to kind of build up noise that we just don't expect, it's a really hard type of class to actually build, the garbage dump class, because we just don't know what's going to be there. So it's kind of interesting that you have that, and it actually seems to be doing reasonable things. I mean, sure, it might be, like the classification between just purely bad or bad contact might be a little unstable, but the fact that it's working is pretty cool.
Yeah, exactly. Definitely something though, would like to refine, but yeah, I think it's the feature. It's just that square wave, because that's kind of like, instead of like applying this, like lots of people take time series and they want to predict the time series. This is more of like a computer vision thing. Like we're just looking at it as the image itself. And yeah, the good stuff, and even this like transients or EM coupling, they have that big distinct feature with a little bit of variables. I think that's how it picks it out. And then bad just is successful because it's like, if it doesn't have any of that, throw it out, kind of thing.
Any other questions from folks?
Another question. I have a comment, because I sort of thought about this problem, and kind of connected to what Doug mentioned, sort of transferability, because at this point it's probably like a 2 second. I think that's
2 second is what we've been.
Yeah, half duty cycle. So, but like, let's say, what if you're using 30% duty cycle somehow, and then I don't know, 5 second off time. So it really depends upon like the case by case. I guess you would change those waveform.
Yeah.
And now I think then you probably need to completely retrain your data. So you need to start from scratch, and then work with the field data, and then do all this time-consuming process of classifying by yourself.
Yeah.
So that seems like but the mathematically that is basically a convolution, right? You got some sort of green function, which contains everything: EM signal, IP signal, DC signal, and then we're just convoluting into, and that's a linear process.
Yeah.
So I thought that somehow if we can kind of integrate that, and then learning at the some sort of that space of green function, and then waveform can be an input of the machine learning, they can potentially can be readily transferable to other types of. That's what I was thinking, and I thought that seems like a bottleneck of using these types of machine learning for like a whole bunch of geophysical data, because it's all convolved by some sort of waveform.
Yeah.
So yeah, it's just a comment I was thinking about. I wasn't sure how to do that, but that seems like a fundamental issue needs to be sort of addressed.
Yeah, and then that's kind of what I was trying to hit on there is, yeah, you know, we have to retrain like every time. So there's got to be a way that we could optimize that somehow and make it transferable, like you said, in like the green domain. And yeah, definitely, hopefully that could be a possibility, because yeah, that's the hard part, is making these data sets. Sure, like every other kind of machine learning problem, it's images, and they've got, you know, there's so many learning data sets out there for how to classify clothes or just images like that, but geophysical data, not so much. So there's going to have to be a nice, smart way of making it transferable. And it sounds like you've been thinking about it already. Got an idea.
Somebody needs to do it.
There is this topic on called transfer learning, which is basically trying to use some convolutional neural network or any other model that you train for a similar data set, that the one that you're trying to apply it, and you can take it as a starting point. So maybe there's also a good thing to look at it.
What that was called, transfer learning?
Transfer learning. It's just basically, so it's like a set of different methods trying to do just what you're explaining. You train your neural network for a similar task, and then you just transfer to a similar task.
Well, that's going to the top of my list then. I'll have to take a look at that.
Yeah, sure.
Yeah, thanks. That's good information.
One other possible connection that comes to mind, and Jorge, I don't know if you've had experience with this either, is I know some of the work in like natural language processing, some of what they try and do is actually build up networks that learn how to predict the next word based on previous words and use that as like a mechanism for translation or understanding a sentence or structure or things like that. And I wonder if there's any concepts with respect to thinking about that with respect to time series.
Yeah. I haven't taken a look at it, but yeah, of course, I think there may be ways to apply it to time series, of course.
Nice. Yeah, that could actually be really good too. Yeah. Looks like we've got some things to try.
Yes, no kidding. Yeah, does anybody else have questions, thoughts you'd like to share with John? We'll of course post this afterwards, so you can follow up and post any questions in the seminars channel on our SimPeg Slack, but I'll give anybody else a minute. Going once, twice, 3 times? All right. Thanks so much, John. That was a really interesting talk. I think there's lots of ideas to continue to explore here. So really appreciate you taking the time to put this together and share with the community today.
Oh, well, thank you guys. Thanks for all the attendance, and yeah, always fun to present you guys.
Excellent. All right. Well, thanks, John. Thanks, everyone. We'll start.